So my role in the Institute for Nanotechnology is that I'm the Director of Educational and Outreach Activities. In addition, I'm a professor in the chemistry department at Northwestern and the chair of the chemistry department. So through the Institute, I'm involved in helping to coordinate a variety of different activities that involve high school students, college students, graduate students, in both formal and informal educational activities. But then, of course, through my other roles, I'm involved in research and discovery of new scientific and technological areas, and also teaching students at a variety of different levels. We have a module that's available for high school teachers if they want to go more in depth on nanotechnology with their students, and that's a materials world module on nanoscience and nanotechnology that the teacher can use for 1 to 5 weeks approximately in a classroom. It's very flexible, so it could be used in a general science curriculum, in a chemistry course, or in a physics course, and adapted to meet the needs of the teacher and what type of curriculum they're trying to, curricular objectives they're trying to meet. What we have here is a solution of gold nanoparticles. These gold nanoparticles each contain between 20,000 and say 100,000 atoms of gold. The solution has this rich red color as opposed to what you'd normally think of gold as being shiny and metallic, because the particles are nanometer size. So this is a fundamental property of the nanoparticles that's very different from macroscale objects, which is that the color of the object actually depends upon its size. So you could imagine if you had a gold coin, even if you cut the coin in half, it's not going to change size. Or if you brought two coins together and made them touch, they aren't going to change in color. But on the nanoscale, that actually does happen. So as we bring nanoparticles together, or as we change their size, the color of the solution actually changes. So to demonstrate this, we take a solution of sodium chloride, which is colorless, it's just a salt solution, and add it to our red nanoparticle solution. And what you see is that slowly a blue color developing, which is most visible down here at the bottom. And that's because as we add the salt, you change the charge on the nanoparticles, and they can now clump together in what's called aggregate. So whereas before we had a red solution, we now have a blue solution of the larger sized aggregated nanoparticles. And eventually, if you add enough of the sodium chloride solution, you then form a black precipitate, which will crash out of solution. So with the red nanoparticles, that solution would be stable for hundreds of years. It's actually the same type of gold nanoparticles that give the red color in stained glass. They're very, very stable in solution. By contrast, once we form these aggregates, the large clumps of them, then this will precipitate out as a black precipitate over the course of hours.